I'm currently a software engineer in Google, and Matthias is an assistant professor in Purdue. This is work that we did in early 2013 when we were both postdocs of Don Song in UC Berkeley. And it came from actually a fairly simple observation. So I should warn you that this is not a very technical paper, but it was meant more as a position paper to outline what we believe are some directions of future research, okay, in an area that hasn't received, like, it's sort of known, but it hasn't received a lot of attention and serious study, okay? And it's about a gap that happens between what a compiler, even when correctly implemented and correctly designed, can give you, and the security guarantees you can put into your code and whether they are preserved, okay? So I'll just give you some examples of this. A couple of them are known, but then there are others that are not known, and that's what we discuss in the paper. And more interestingly, we said, all right, like, people know about these examples, but have they been studied? So we undertook some analysis, and I'll give you a summary of that. And the main conclusion is really that there's a lot of work to do in the future. Okay, so whenever talking about compilers, it's one of the oldest, compiler construction is one of the oldest fields in computer science, and the problems are very, very hard. And we'll see that, you know, like all the great giants of computer science have been inspired by problems related to compiler construction. And it's often taken very long time to find solutions. So one of a prominent example of somebody talking about this is Ken Thompson in his Turing Award lecture, where he said, you know, do you trust your compiler? And he gave a specific example of how a compiler could introduce a Trojan, right? And he put out there this question, and it's hard to find people who have explicitly expressed the same concern, but a lot of people have worked around it in the same way. And one of the earliest cases is in the implementation of the Lisp compiler. John McCarthy and James Painter talked about the correctness just of the expression compilation part. Okay, and this is in 1967. And since then, there's been quite a lot of work. And in the last 15 years, we actually have tools. So there are a whole bunch of tools to do compiler testing. And the formal methods people, including me, I belong to that community, has also done a lot of work on formally verifying. And in fact, Xavier Leroy in the last few years has implemented an entire compiler within a theorem prover. So I can recommend the papers mentioned at the bottom here, the one on taming compiler fuzzes for an overview of the testing side, and the paper on the other side for an overview of formal things. And if you look at the second paper, it opens with more or less the same line that's there in Ken Thompson's Turing Award lecture, which is, can you trust your compiler? So do we conclude from this that nothing happened in the 25 years since that Turing Award in this paper? No, I mean, what happened is this is one specific solution to the issue of trusting a compiler that he's presenting, that he spent more than 5 years working on, okay? And what I want to talk about here is that there is one community that believes that there is one solution they have found, but there are other aspects, and the issue of what does trust mean goes pretty deep here. And let's look at a couple of examples. So this is from the GCC mailing list from as early as 2002, where somebody says, well, look, here's a small snippet of code where I want to manipulate a password or a password hash in memory. And I want to, you know, scrub the memory before I return. And from the compiler's point of view, the memory scrubbing operation, the result of that is never used in computation anywhere. So it's perfectly fine to remove that to save some load and store operations, just from a performance point of view, okay? And now, of course, this is because the compiler doesn't know the security intent of the programmer. This is a well-known example, but even there, it took a long time, and still there isn't a clear agreement on, you know, who should address this. So if you look, there's a lot of heated debate, right? And people with security concerns have valid points, and people coming from the compiler point of view have valid points as well. And what we decided to do is not actually to take a position on the debate, but to say, look, there are two different positions here, and there's a gap between what they believe the compiler should give you, right? And let's study this gap very seriously, right? And this is the gap between the correctness and the security points of view. That's what we were doing. And more generally, we can ask the question of, can a correctly designed and even correctly implemented compiler optimization violate some security guarantee you put in your code? And if you look in the literature, just for the example that I gave you, it took a long time to have reusable techniques to prove correctness of compiler optimizations. But in the last few years, all these papers will give you correctness of the dead store elimination that I mentioned in the beginning, okay? So the answer to this question is yes, we have an optimization. It has been correct. It has been formally verified. It has been correctly implemented, and it's clear that it violates some security guarantee that somebody wants. Okay, and this is an instance of what we call in the paper the correctness security gap. Okay, but more interestingly, what we wanted to then understand is how prevalent is this. So the example that I gave you is on the GCC mailing list over 10 years ago, and there are a couple of related examples that are well known. But what are other examples people might not have thought about? And more importantly, it's all very well to say, okay, there is this and try to play the blame game, but why does this arise? Because, you know, there's something slightly paradoxical in this situation, right? We have a hardcore, formally verified proof done within a theorem prover that has been developed for many years and is obviously correct. But then there's our intuition of semantics preservation that's being violated here. So what gives? Okay. So in the paper, we looked at a few different gaps. So you might have code that defends against memory-related security issues or against side channels. And then we identified compiler optimizations that may violate the security guarantees that you have put in along those dimensions, okay? And there are also language-specific issues of which we only look at undefinedness in C and C++. Okay, and what I will do for the rest is just look at a couple of these examples. There are more in the paper, so you know, if you find it interesting, please go and read. So here's an example where it's a very toy example, and it's deliberate, and I'll come back to this point in a moment. But you may write some code that works in an unsecure environment, and then all computation that is expected to execute in a secure environment might be put into a separate function that is called at some point. So what's happening here is a coding pattern where you use constructs that the programming language gives you, which is basically function boundaries, to enforce a trust boundary, right? So a stack frame. Now, nothing stops the compiler from trying to inline the first function, in which case the data and computation that is assumed to execute in a secure stack frame and environment will now be merged with stuff that is not assumed to execute in a secure one. Okay, so this is just one example. So another category is side channels, especially in cryptographic code. People do things like write code using inline assembler to make sure the timing of various operations, you know, doesn't give rise to a side channel. So this is a lot of work, but the problem is that such code is not always portable and it's very brittle. So when possible, you would like to use higher language coding, provided that the semantics of the language gives you some guarantees on timing. So here's again a toy example where we have two branches, and on both sides they have the same structure because you try to preserve the timing because they're very simple operations. And what might happen is in the else branch, the compiler might simplify and say, well, there's a common expression occurring in all these three. We can factor it out. And then what happens is you have simpler code, but then the timing of the code is off now, right? So more generally, you might write code with a certain intent. Compiler is not guaranteed to preserve it. Undefinedness, there are many examples. This is one of the better known cases. This is actually from the Linux kernel mailing list. This is from the Linux kernel, and you'll see this article that you can read about it here. But what happened was somebody actually patched a bug by introducing the box in the first line, that line. And what happens is now there is a check if there's a check that a pointer is not null. But then that pointer is actually dereferenced before. So GCC concludes that, you know, if that pointer dereference didn't result in a crash, then the second check is not even required. So it would eliminate that check and just return that. Okay. So this situation is a bit subtle because from the compiler's point of view, they're allowed to do that because dereferencing a null pointer is undefined behavior, and compilers interpret it in the most opportunistic way they can. In this specific case, you can read in this article, combined with a few other effects, it leads to a privilege escalation bug in the Linux kernel, okay? And like in this case, it was even an exploitable vulnerability, okay? And so this returns to the point in our paper and in this presentation, I have a lot of toy examples, right? By themselves, it's difficult to construct an exploit out of something that small. But in a context where a few other dominoes might fall, you may be actually able to set up an exploit. And Linus himself has written about this, right? This is one of his biggest complaints with GCC in the way it's interpreting and modifying code in the presence of undefinedness, okay? And so again, we have a gap between the way a compiler optimizer interprets semantics and somebody caring about security might do that. And in the specific case of undefinedness, there was actually a cool paper in 2013, concurrent to the time we did the work, but it's quite different in that they have a tool and it finds a lot of such bugs, and it takes that one specific point and studies it in great depth. So let's look briefly at where this kind of comes from. I've given you a couple of examples, but all of these are actually things that have formal correctness proofs. So what we wanted to understand was what's going on here. Why can't I rely on that correctness proof to preserve the security guarantee I put in my source? Okay, and the main observation is that correctness proofs rely on some notion of preserving the behavior of the program, and the behavior is defined with respect to a notion of execution. So let me walk through this, abstracting as much as possible as I can, formal semantics issues. But here's a simple optimization where you replace a redundant variable and just return the result of incrementing a variable. And I'll walk you through what the semantics might look like. So here is a calling context. You have a call stack, and you have a program counter, a variable x that is 5, and a variable y that is 10. And suppose you say y is equal to increment of x. Suppose you do that. Then what happens is you push something on the call stack, you have a and b, you increment b, and then you return it, and that's what you get at the end. Okay, this is in gory detail walking through every state of the execution. And if you take the optimized code on the other side, what we'll have is that we just have one step in the computation, right, and then you increment it. And sort of the essence of these proofs is that you have a sort of diamond here, right? Is that it doesn't matter what intermediate states you went through, but you begin and you start in the same state. And this is the essence of a compiler correctness argument, okay? That you could take two different paths. One is through the unoptimized code and the other is through the optimized code, and they'll give you the same result. And there are a lot of proof techniques that go by the name of simulation, bisimulation, logical relations, and so on, that allow you to do such reasoning. Okay, and so the main observation I want to have here is that when you do optimization, the reason about correctness, we have some source code, and we reason about it with respect to what I would call the abstract machine, which is the machine with respect to which the programming language semantics is defined. But when you reason about exploits and vulnerabilities, you don't reason about some abstract machine. It actually runs in a concrete machine, in a concrete operating system. So there's a different machine here, and there's a different reasoning that's going on. Okay? And in particular, what's happening is that the attacker is reasoning with a machine that has artifacts like persistence in memory, timing, and so on, which are not even captured by the machine that is used when defining language semantics. And therefore, these artifacts don't even exist at the level of the proof. Okay? So one could ask, does this mean that 40 years of work in compiler correctness and so on are completely useless, right? Is there nothing that we have gained from it because we've been using the wrong machine model? So let me try to redo that proof using a slightly different machine model. And the only difference I've made here is that in practice, we don't actually have a stack that works like a stack data structure, but we have memory and we have a pointer, right? So let me just mimic that here with the red box that is saying where the stack pointer might be. Everything else is the same as what we had before. The only difference is that in the final state, the pointer has gone down, but the previous stack frame would still be there. Okay? And now what happens is if I compare the code before and after the optimization, we can see that even though I have the same state at the end when I return, the part that is not visible is actually different, right? So if you use a different machine model, you can see that the final states that you would get are different, and so you would not be able to complete the proof. And so actually the good news is that if we look at this picture, and we tried a few other examples, so there are these sort of inputs to your proof. There are the programming language and the machine semantics, and then there's the proof technique itself. And what I did here was I used the same proof technique. I walked through the same thing, and it didn't work out. So the good news is that it is not our proof techniques that are broken. The proof techniques are all fine. What we need is better, more accurate machine models, right? And if we can change our machine models that we use in the proof, maybe we can make clearer conclusions with respect to security. So I talked about, these areas, and there is the paper from the group at MIT from SOSP 2013 that very seriously studies the undefinedness. But basically, in every case here, there is a relationship between the optimization and its impact on security, and there's a lot to study over there, right? So specifically, we can have testing tools in all these cases to find out if the optimization modified a security guarantee in the source. Another thing which we believe has to be studied in the future is currently we have a lot of work developing and writing down models, abstract semantic machines, right? And this is not just if you want to do correctness proof, even if you do things like symbolic execution, right? You need a notion of a machine that you use. And now if you want to use symbolic execution to find these kind of issues, you need to capture some semantics of the machine. And if you want to do things like side channel attacks, you need timing in your machine. So you need a lot of different machine models. And finally, correctness proofs are described in terms of, well, is this optimization correct? But we might more precisely want to ask, is this optimization oblivious to an attacker who's looking at a machine, right? And the point is, this is a question that would strictly generalize in a precise sense the way compiler correctness is done today, because current compiler correctness is just code in a specific machine with a specific notion of observation. And one thing we observed in the paper is that there is a strong analogy to the situation with relaxed memory models. At some point, you had architecture that had multiple cores, and then you had relaxed memory models, and then they realized that a lot of the optimizations or analyses in compilers might not give you the same soundness on these new memory models. And then a lot of work was done on having testing tools to figure out if there is an error, on having a notion like memory barriers, and doing new formal work. In a similar way, there's a whole research program, we believe, to pursue, to study this graph, to identify when these kind of bugs happen, to introduce barriers to fix them, because you don't want to turn off all optimizations in general, to develop new machine models, and so on. So that's more or less our position on this, and I think that's a good point to stop and take questions. Thank you. Does somebody have a microphone?
Hi, thanks for the talk. Near the end, you said, is the optimization observable to an attacker who can monitor the machine, right? And I'm a little worried about that because I can't imagine an optimization that would not be observable to an attacker monitoring the machine. If you model the machine with high fidelity, right? Like if the attacker really can look at arbitrary memory and the program counter and things like that, it seems unbelievable to me that there could be an optimization that does not change the attacker's view.
Okay. So I was using the term observable and attacker actually in a very formal sense, meaning not an attacker like us and not an actual machine, but you could assume, the same way you do attacker correctness proofs for security protocols, where you say there are certain things an attacker can and cannot do, and there are certain things an attacker can and cannot observe.
Right, but one of the...
So in this case, I would say there's only some part of the state of the machine that the attacker can observe, right? So when you say with high fidelity, right? Sorry?
But it included memory.
It included memory, but it doesn't have to include the entire memory, right? It doesn't have to include the entire memory everywhere. For example, you could say you can observe the top of the stack or the top and everything before, but not, whatever's actually on the stack. So that's what I mean. In general, what you're saying is right, but that also leads you to a situation where you can't do any optimizations, right?
Right, exactly. So what I was trying to get at maybe is like a distinction between like some states of the machine, it does, like if the attacker sees it's in state A versus state B, that's not a security problem. And some differences, it is a security problem. And I think that's what needs to be modeled, that
Right. So, and
When
in
you're
fact,
optimizing, don't
that is what I
optimize
mean.
away the security critical bits, right?
No, no.
Somehow.
So actually, when you say, that is not a problem, why is it not a problem? So there is some aspect of the states that's irrelevant to any problem that you care about, right?
Right.
And I would say that's part of what you don't need to observe.
Right.
And I would factor that into the observation.
Okay, good, thanks.
It seems that a lot of the problems that you describe come from the semantics of C and C++ not matching what programmers think. And possibly instead of trying to modify the machine model, what you can do is try to figure out what programmers actually think the semantics of C and C++ are and have a compiler that tries to respect those instead of the strict language standard. How much benefit do you think that would have?
So, I mean, that's not strictly true for all the optimizations. So that's true for issues like undefinedness, right? Where people might assume different things happen when something's undefined. But if you look at the dead code case, I max out something in memory. And so, is the result of calling a function the actual value, or should the programmer suddenly start to believe? I don't even think it's true that most programmers would believe that when I call some function, my result is the entire memory state that persists after I've called that function, right?
Yeah.
So I would actually disagree there in that, or I don't even think that most programmers would have an agreement on what's happening there.
Right.
So in very specific contexts, you care about the memory state, not in general.
It'd be interesting to see what can be done by that kind of approach versus the other.
Yes.
Any other questions? I actually had one. Your observation about side effects particularly, hit home. I noticed how, the second computational model that you introduced was actually tracking the side effects in the, in the state of the variables. And when I was talking earlier about parsing being, a type construction operation that eliminates strings and introduces some type, the thing I didn't say, because I tend to think like a functional programmer, is you want that function to be pure. You want it to not introduce side effects. You want it to not, it should not go and jump to some other region of memory and read the shellcode that's been inserted by a previous, by a previous thing. So what I'm wondering is anybody taking a look at compilers from an effect systems perspective?
Sorry, do you mean?
Effect systems as the analogy to type systems, but studying the side effects of computation. I mean, that may just be an out of the an out from left field question. You might not know anything about that.
Right. Yes, I think I'd have to think and do some background work. But my knee-jerk answer is sort of like, I feel like compilers are all about the side effects, right?
Yeah, I feel like it ties right into what you and Ian were talking about.
Messing around with the side effect to make sure the effect itself is efficiently visible.
And which side effects do we care about and which ones do we not? We really want that password memory to be zeroed out, and so we don't want that to be optimized away, so we have to preserve that side effect, but other side effects we don't care so much about. Any other questions? All right.
So I'm not really too much of a low-level guy, but I've been reading some blog posts recently. Rob Graham wrote a post about, not even being able to trust assembly code because of all the pipelining and things going on. So to what degree, how serious is that, and to what degree do we need to be worried about that? So even when we get compilers producing code that we think matches the high-level model of what we think it should do, but what do we do about the hardware issues? I suppose that's completely separate, but
So I would say I could do this entire talk, right, with starting at the assembly level, right? Because Matthias, in fact, forwarded me that blog post once and said, assembler is the new high-level language, right?
Right,
Exactly. So all of these issues kind of apply. But on the other hand, that's not terribly bad. I think kind of what we're saying is that once we start studying this seriously, hopefully the techniques are reusable, right? So the kind of so the specific models you may have to redevelop, But the rest of the pipeline of how to analyze and understand and find these gaps and the bugs, hopefully that's reusable at the assembly level, right? And of course, there's a huge cost to pay in terms of analysis and time, and I think that just depends on context and application, whether you want to pay that. But like our point is that we should at least know that we can pay for, that answer.
All right, let's thank our speaker again.